Hello, welcome to another module in this massive open online course. All right. So we are looking at the Z transform and its various properties. Let us continue our discussion with the system function for a discrete time LTI system. Okay. So we want to continue our discussion on the Z transform by looking at the system of, because remember Z transform is used to analyze discrete time signals and systems. So, we want to look at the system transfer function of a discrete time or of discrete time LTI systems. And similar once again to the discussion on the Laplace transform, but this time considering a discrete time LTI system and discrete signals. So, we have x n which is given as input to a discrete time LTI system with impulse response. So, this is your impulse response of the discrete time LTI system, and the output is y n. So, we are considering an LTI system with impulse response h n, and x n is the input to this LTI system and y n is the corresponding output. Then we know that the output y n is given as the convolution of the input with the impulse response. So, what we will have is that y n equals x n convolved with h n, and from the previous properties of the Z transform we know that convolution in time is basically multiplication in the transform domain. Therefore, from the properties of the Z transform the Z transform, what follows is that y of z equals the multiplication of the Z transforms x of z times h of z, implies the transfer function h of z equals y of z divided by x of z, okay, where h of z, remember h of z, this is the Z transform of the impulse response h of n. That is the impulse response of the LTI system. At this h of z is known as, this h of z is known as the system function or the transfer function. This is known as the system function or the transfer function of the discrete time LTI system. Okay. Now, let us look at the properties of the discrete time LTI system based on its system function or the transfer function. Okay. So, what we want to explore now are the properties of the LTI system. So, we want to look at the properties of the LTI systems. The first property is causality. Okay, we want to consider a causal LTI system. So, the First property is causality. This implies that Hn equal to 0 correct. So, an LTI system is a causal system if the impulse response is 0 for n less than 0, that is the discrete time impulse response h of n is 0 for n less than 0, it is non-zero only for n greater than or equal to 0. Now, this means that Hn you can see is a left handed is a right handed signal, therefore, the ROC, the region of convergence of the Z transform h of z must be of the form magnitude Z greater than R max, where R max, remember, as per the properties of the ROC, is the maximum of the poles of h of z. So, this implies h of n equals a right sided or right handed signal. Implies ROC must be of the form magnitude of Z greater than R max, where R max, remember from what we saw yesterday from the properties of the ROC, if you remember from the properties of the ROC, for the right handed signal magnitude of Z must be greater than R max, where R max is the largest magnitude of the poles of x of z, that is the largest magnitude of poles of x of z. R max is the poles of h of z, where h of z is the transfer function, that is what we have just seen. So, the ROC is of the form magnitude h, magnitude z is greater than R max. Now, let us look at stability, that is the other important thing, stability. Now, for the system to be BIBO stable, remember stability, one of the most popular definitions is BIBO stability, bounded input, bounded output stability. Bounded input, bounded BIBO stability. For BIBO stability, we require summation over all n, that is n ranging from minus infinity to infinity, magnitude summation of magnitude of h of n must be less than infinity, that is it must be this quantity must be a finite quantity, cannot be an infinite quantity, it has to be a finite quantity. Okay. Now, we can show that this implies that for a BIBO stable system, the transfer function, that is h of z, must include the unit circle in its ROC, that is in its region of convergence. So, this implies, and this can be easily shown, which we are going to show shortly, that is for a system to be BIBO stable, that implies h of z must include the unit circle remember unit circle is all the values of z which are of the form z equals e raised to j omega, that is magnitude of z is 1, that is unit magnitude any arbitrary phase. So, that is unit circle comprises of all z, all values of z such that z equals e power j omega, that is basically satisfying the property magnitude of z equals 1, that is r equals, remember every z can be represented in polar coordinates as r e raised to j omega. If r equals 1, which is the magnitude of z, then that corresponds to a z on the unit circle. Okay. Now, let us look at h for a stable system. Let us look at for a BIBO stable system. Let us prove this, and the proof is very simple. So, magnitude h of h e raised to j omega for any z on the unit circle equals, well, n equals minus infinity to infinity h n z raised to minus n, that is e raised to minus j omega n. So, magnitude h of e raised to j omega, this will be magnitude e raised n equals minus infinity to infinity h of n e raised to minus j omega n. Now, the magnitude of a sum is less than or equal to the sum of its magnitudes. So, this is less than or equal to summation n equals minus infinity to infinity magnitude h n minus e raised to magnitude. Now, this quantity is 1, magnitude e raised to minus j omega 1. So, this is n equals minus infinity to infinity magnitude h of n, which we know, since the system is BIBO stable, we know this quantity is less than infinity, that is, this is a finite quantity. This quantity is a finite quantity, and therefore, this implies magnitude e raised to j omega is less than or equal to a finite quantity, which implies magnitude of h raised to, because this is greater than or equal to 0, this is positive quantity because this is a magnitude. So, this is less than, which means that this is equal to a finite quantity, which means that this has to converge for every z equal to e raised to minus j omega, and it has to be a finite quantity. Therefore, z equals e raised to j omega for every omega is in the region of convergence, which means the unit circle must be in the ROC for a BIBO stable LTI system. So, this implies that for all omega, which implies e raised to j omega belongs to ROC, element of the ROC, right, e raised to j omega belongs, set notation, belongs to ROC for all omega, for every value of omega, which implies that the unit circle is in the which implies that the unit circle belongs to the ROC for a BIBO stable system. Okay, so, the ROC. So, for a BIBO stable system, the system transfer function h of z must include the unit circle in its ROC, region of convergence. Okay. Now, let us look at the system function for an LTI system described by a difference equation. So, what we want to do, and this is again fairly simple. For an LTI system, described by a difference equation. So, this is the system function for an LTI system described by the difference equation. Consider an input x n and output yn. Then the difference equation representation is given as follows: summation k equals 0 to n ak equals yn minus k summation k equals 0 to m bk n minus k. Now, this is known as a difference equation. Now, typically for a continuous time LTI system we have a differential equation, correct. We have seen summation ak d raised to k, that is the kth derivative d of d raised to k yt over dt k equals summation over k from 0 to m bk d raised to k xt divided by dt, that is dt to raised to k, that is the kth derivative of x of k, that is a differential equation, correct. This is a difference equation for for discrete time signals, okay. This is a difference equation. Now, in a difference equation typically we have, now taking the z transform on both sides, taking the z transform on both sides we have summation k equal to 0 ak, remember the z transform of yn minus k, that is yn delayed by k is yz, z raised to minus k equals k equals 0 to m bk xz, z transform of xn minus k is xz, z raised to minus k, which means if you take yz common on the left, that is summation k equals 0 to n ak z raised to minus k, this is equal to, take xz common, xz summation k equals 0 to m bk z raised to minus k, which implies that yz over xz equals hz. This is, well, this is summation k equals 0 to m bk z raised to minus k divided by summation k equals 0 to m, or k equals 0 to n ak z raised to minus k. So, this is basically your hz, which is in the form of a rational transfer function. You can see this is in the form of a rational function in B. So, it is a rational so this is a rational transfer function, and taking the inverse Z transform one can obtain the impulse response of the system described by this difference equation. Okay. So, we have the Z transform, okay, we have the Z transform of the system described by the difference equation, all right, and we can see that it is given by a rational transfer function, all right. Okay. So, this is basically your Z transform, which is given by a rational transfer function, all right. So, that completes our discussion on the definition, properties, the definition and the properties of the Z transform as well as the analysis, all right. So, subsequently in the modules that follow, we will look at several problems for the application of the Z transform on to understand the various properties and its application. Okay, all right. So we'll look at other aspects in the subsequent modules. Thank you very much.